What if the act of looking at something changes what it is? In 1957, a physicist named Hugh Everett proposed something strange. He suggested that when we measure a particle, reality does not collapse into one outcome. Instead, all possible outcomes happen, each in its own branch of existence. This theory, called the many worlds interpretation, remains one of the most debated ideas in physics. Some scientists embrace it, others reject it entirely. Hugh Everett walked into his Princeton advisor's office in 1957 with an equation that would rewrite existence. He had solved quantum mechanics, he claimed, and the answer terrified him. Every textbook said particles collapsed into one state when observed. Everett proved they never collapse at all. Reality itself splits instead. His advisor, John Wheeler, nearly rejected the thesis. The implications seemed impossible. If Everett was correct, then every quantum interaction created new universes, not metaphorical universes. Actual physical realities branching off from ours like roads diverging in a forest. Wheeler worried about his student's reputation. He urged Everett to soften the language, make it sound less radical. Everett refused. The mathematics were undeniable. When you measure an electron, you do not force it to choose a position. You become entangled with it. One version of you sees the electron here. Another version sees it there. Both versions are real. Both continue existing in separate but parallel worlds. This is not philosophy. This is what the equations describe when you follow them honestly to their conclusion. For decades, physicists ignored Everett's work. It sat in obscurity while others proposed elaborate explanations for quantum behavior. They invented invisible waves guiding particles. They suggested consciousness played a special role in physics. They added arbitrary rules about when and why things collapsed. All of these attempts required adding something extra to the equations. Everett's interpretation required nothing extra at all. Then David Deutsch at Oxford picked up Everett's work in the 1970s. Deutsch realized something profound. If parallel worlds exist, they could explain why quantum computers work. A quantum computer with just 300 quantum bits would process information equivalent to more particles than exist in the observable universe. Where does that processing power come from? Deutsch argued it borrows computational resources from parallel universes. The computer reaches across realities to solve problems. The scientific community began taking Everett seriously. His mathematics predicted testable results. Experiments with quantum entanglement confirmed particles behave exactly as Everett described. When two particles interact, they remain connected regardless of distance. Change one and the other responds instantly. This should be impossible if only one reality exists. The connection makes perfect sense if both particles exist across multiple branching worlds simultaneously. Today, research teams at Caltech, MIT, and Oxford treat Everett's many worlds interpretation as a leading candidate for how reality actually functions. The theory explains quantum mechanics without adding mysterious elements. It accounts for experimental results that baffled physicists for a century. Most striking of all, it makes a specific prediction that other interpretations cannot. If you could build a quantum computer sophisticated enough to be conscious, Everett claimed it would remember existing in multiple states at once. What Everett discovered goes beyond abstract physics. If his equations are correct, then you split every time your neurons fire. Every decision creates branches. Every moment multiplies you across countless parallel worlds. The question is whether we will ever find direct proof. Strange signals in the cosmos suggest we might already have it. Picture a single electron moving toward a barrier with two slits. Classical physics says it must go through one slit or the other. Quantum physics reveals something far stranger. The electron passes through both slits simultaneously. When it strikes a screen on the other side, an interference pattern emerges. Waves from both paths overlap and create bands of light and shadow. This experiment has been repeated thousands of times. The electron genuinely exists in two places at once. Now, scale this up. An electron is made of quantum fields. So is every atom in your body. So is every molecule in the air around you. Each particle exists in superposition until it interacts with something else. When interaction occurs, something remarkable happens. The wave functions do not collapse. They merge. Two particles touch, and their separate descriptions become one combined description. Physicists call this entanglement. Once entangled, you cannot talk about particle A without also talking about particle B. They become a single system even if you separate them by millions of miles. Measure particle A and you instantly know information about particle B. Einstein called this spooky action at a distance and believed it proved quantum mechanics was incomplete. He was wrong. Entanglement is real and verified in laboratories worldwide. But here is what makes it extraordinary for our discussion. Every time particles entangle, the universal wave function splits. One branch contains the outcome where particle A spins up. Another branch contains the outcome where particle A spins down. Both branches are physically real. Both continue evolving according to the same laws of physics. You just cannot perceive the other branch because you became entangled with particle A in this specific way. Think about how often particles interact. Photons from your screen strike electrons in your retina. Those electrons trigger chemical reactions in your optic nerve. Signals propagate through neurons in your brain. Each step involves trillions of quantum interactions. Each interaction entangles more particles. Each entanglement splits reality. The splitting never stops. Right now, at this very moment, cosmic rays from distant supernovae are colliding with molecules in Earth's atmosphere. Each collision spawns new branches. Radioactive atoms in rocks beneath your feet decay randomly. Each decay creates parallel worlds, where the decay happened at different times or released particles in different directions. The universe branches quadrillions of times per second just on Earth alone. Multiply this across every star, every planet, every galaxy in observable space. The rate of splitting becomes incomprehensible. David Deutsch estimates that even simple quantum systems generate branches faster than we can count. A universe with 300 particles in superposition creates more branches than there are atoms in our entire observable cosmos. You might wonder where all these universes fit. The answer lies in the structure of quantum reality itself. They do not exist elsewhere in three-dimensional space. They exist in quantum configuration space, a realm with far more dimensions than our familiar three. Every branch occupies the same physical location we do. They overlap perfectly, but remain causally disconnected, except in rare moments when interference occurs between worlds. Those moments might explain phenomena we cannot otherwise understand. In 2004, NASA's Wilkinson Microwave Anisotropy Probe mapped the oldest light in the universe. The cosmic microwave background glows from every direction, a relic from when the cosmos was 380,000 years old. Temperature variations across this ancient light reveal how matter clumps together to eventually form galaxies. Most of the map looks smooth with tiny fluctuations. Then astronomers notice something deeply wrong in the southern sky. A region 5 degrees across, roughly 10 times wider than the full moon appears from Earth, registered significantly colder than surrounding areas. Not slightly colder. This zone measured 70 microkelvin below the average temperature. In some spots, it dropped 140 microkelvin colder. The variations elsewhere in the cosmic microwave background barely exceed 18 microkelvin. Scientists call it the cold spot. Standard cosmology predicts fluctuations this large might appear across areas 1 degree wide. They should not span 5 degrees. The probability of such a large cold region forming randomly sits around 1 to 2%. Possible, technically. Unlikely enough to demand explanation. Initial theories focused on a supervoid. Perhaps a massive region of space between us and the cosmic microwave background contains far fewer galaxies than average. Light passing through this void would lose energy, appearing cooler when it reaches our telescopes. In 2015, researchers claimed to find evidence for this Eridanus supervoid. The structure would stretch 500 million to 1 billion light-years across. If confirmed, it would rank among the largest structures humanity has ever identified. But then Durham University conducted a detailed survey. They used the Anglo-Australian telescope to map galaxies around the cold spot. They compared this data against the Gamma survey, which had catalogued galaxies in other parts of the sky. The results, submitted to monthly notices of the Royal Astronomical Society in 2017, contradicted the supervoid hypothesis entirely. Galaxy distribution around the cold spot looked normal. Nothing special. No giant void existed there. The Durham team reached a troubling conclusion. If no supervoid caused the cold spot, then something in the early universe must have created a genuinely cold region. But what? Standard models of the Big Bang cannot produce cold patches this enormous. The temperature variations should smooth out across such large scales. Something violated the expected physics. One explanation stands out as particularly bold. Cosmologist Laura Massini-Houghton proposed that the cold spot represents a scar from when our universe collided with another universe during the inflationary period. In the first fraction of a second after the Big Bang, space expanded faster than light. If eternal inflation theory is correct, this process created countless bubble universes. Some bubbles could have collided with ours before inflation separated them permanently. A collision would send a pulse of energy rippling across the universe, like a wake behind a ship. This wave would alter the temperature of the cosmic microwave background in a specific pattern. The cold spot's shape and temperature profile match theoretical predictions for such a collision. The probability remains extremely small, but if other explanations fail, we may be looking at physical evidence that parallel universes are not theoretical constructs. They might be touching us right now. The cosmic microwave background carries information from the earliest moments of accessible time. When the universe cooled enough for atoms to form, light broke free and began traveling through space. That light has been journeying toward us for 13.8 billion years. We see the universe as it appeared when it was just an infant, long before stars or galaxies existed. Think of the cosmic microwave background as a photograph. Temperature variations in this photograph show density fluctuations in the primordial plasma. Regions that were slightly denser became the seeds for galaxy clusters. Regions slightly less dense became cosmic voids. The pattern reveals how structure emerged from an initially smooth universe. Scientists can predict what this pattern should look like. Our best models of cosmology, refined through decades of observation and calculation, tell us the temperature variations should follow specific statistical rules. When we measure the actual cosmic microwave background, it matches these predictions almost perfectly. Almost. The cold spot does not fit. Here is why this matters. If the cold spot came from normal quantum fluctuations in the early universe, we should see similar anomalies elsewhere in the sky. Large cold regions should appear with some frequency. Yet the cold spot stands alone, unique, isolated. This uniqueness suggests something unusual happened in that particular direction. Matthew Kleban, a physicist at New York University, created detailed mathematical models of what a universe collision would look like. When two bubble universes touch, they release energy at their boundary. This energy propagates outward as a spherical wave. From our perspective, inside one of the bubbles, we would see a circular pattern in the cosmic microwave background. The pattern's size depends on how far away the collision occurred in space and time. Kleban's calculations predict a cold region with specific geometric properties. It should appear roughly circular. Its temperature profile should show a particular gradient from center to edge. The cold spot matches these predictions reasonably well. The fit is not perfect, but it is close enough to warrant serious consideration. European Space Agency's Planck satellite, launched in 2009, provided even more detailed maps of the cosmic microwave background. With resolution 3 times higher than earlier missions, Planck could reveal fine structure that previous telescopes missed. If the cold spot was just noise or instrument error, Planck would expose it. Instead, Planck confirmed the cold spot's existence and sharpened its boundaries. Researchers analyzed the Planck data, searching for signs of multiple universe collisions. Some theories predict eternal inflation should have caused numerous collisions, not just one. Early claims suggested possible evidence for 4 separate collision signatures. Later analysis found these signals fell within the range of random statistical noise. No definitive proof emerged. The cold spot remains the strongest candidate. It sits at the edge of what standard cosmology can explain through chance alone. Some scientists argue we should not invoke exotic physics for a 1% probability event. Others counter that 1% is small enough to explore alternatives. Professor Tom Shanks from Durham University stated the stakes clearly. If further analysis rules out all conventional explanations, then the cold spot might be our first evidence that other universes exist. What we need now are additional ways to test this hypothesis. Quantum mechanics reveals that particles do not have definite properties until something forces them to choose. An electron does not have a specific position or momentum. It exists as a wave of probability spread across space. Only when we measure it does the electron appear to occupy a single location. This seems bizarre because nothing in our daily experience behaves this way. A coffee cup sits on your desk. It does not exist in multiple places simultaneously. The key difference is scale. Tiny objects like electrons can maintain superposition. Large objects made of countless particles lose superposition almost instantly through interaction with their environment. Physicists call this decoherence. The surrounding environment constantly measures large objects through countless tiny interactions. Air molecules bump into things. Photons bounce off surfaces. These interactions entangle the object with its environment and destroy quantum effects. But superposition itself is completely real. The double-slit experiment proves this beyond doubt. Send individual electrons one at a time through 2 slits. Each electron creates a single dot on the detection screen. After many electrons, an interference pattern emerges. The only way to get interference is if each individual electron passes through both slits. The electron exists in superposition, taking both paths simultaneously until it hits the screen. What makes superposition relevant to parallel universes is what happens when we try to observe which slit the electron uses. Place detectors at each slit to measure which path the electron takes. Suddenly, the interference pattern vanishes. The electron now goes through one slit or the other, but never both. Observation changes the outcome. Traditional interpretations claim observation collapses the superposition. The electron was in multiple states, and our measurement forced it to pick one. This raises uncomfortable questions. What counts as observation? Does it require consciousness? Where exactly does the collapse happen? Why do the equations of quantum mechanics say nothing about collapse? Everett's many worlds interpretation offers a radically different answer. The electron never collapsed. You did. Before you measured which slit the electron used, you existed in superposition too. One version of you detected the electron at slit A. Another version detected it at slit B. Both versions are real. Both exist in separate branches of reality. From each branch, you see the electron going through only one slit because you became entangled with it. This applies to everything, not just electrons. When light enters your eye, photons interact with molecules in your retina. Those molecules change shape and trigger nerve signals. Each step involves superposition. Each measurement you make entangles you with the measured object. You split into versions that saw different outcomes. The universe exists in superposition at every level. All possible arrangements of matter and energy coexist in the universal wave function. We perceive only one arrangement because we are part of the system. We cannot step outside to see the full superposition. We ride one branch while countless others diverge around us. If this seems impossible to accept, consider that quantum superposition has been directly measured in laboratories for particles, atoms, and even small molecules. The mathematics works perfectly. The experiments confirm the predictions. What remains controversial is whether this scales up to include human observers and entire universes. In 1926, Erwin Schrödinger wrote down an equation that governs how quantum systems evolve over time. This equation takes a wave function as input and tells you how it changes from one moment to the next. For a single particle, the wave function describes all possible positions and momenta the particle could have. The equation never includes anything about collapse or measurement. It just describes smooth, continuous evolution. What happens when you apply the Schrödinger equation to multiple particles? The wave function becomes more complex. Instead of describing one particle's position, it describes all particles' positions simultaneously. This joint wave function captures correlations between particles. When particles interact and become entangled, the equation automatically accounts for this through the structure of the wave function. Now ask a bold question. What if you apply the Schrödinger equation to every particle in the universe? You get a single universal wave function that describes the state of all matter and energy everywhere. This wave function evolves deterministically according to the equation. No randomness, no collapse, no special rules for observation. Just one mathematical object changing smoothly in time according to known laws. This is the theoretical foundation of the many worlds interpretation. The universal wave function is reality itself. Everything that exists, has existed, or will exist is encoded in this mathematical structure. When we perceive the universe, we perceive one tiny slice of the wave function. We see one branch. The other branches remain just as real, but forever beyond our direct perception. The wave function has an almost unimaginable structure. It exists in configuration space, a realm with 3 dimensions for every particle in the universe. Our observable universe contains roughly 10 to the power of 80 particles. The configuration space for our universe therefore has 3 times 10 to the power of 80 dimensions. Trying to visualize this space is hopeless. Even the most abstract mathematical representations fall short. Despite this complexity, the wave function obeys relatively simple rules. The Schrödinger equation determines exactly how the wave function changes. Given the wave function now, you can calculate it at any future or past time. The evolution is reversible. No information is ever lost. Every event that occurs in one branch is balanced by complementary events in other branches. This raises a philosophical question. If the wave function contains all possible outcomes, does anything truly happen, or does time itself become an illusion? Some physicists, including prominent advocates of many worlds like Sean Carroll, argue that time remains real. Events still occur in sequence within each branch. The branching itself happens in time. We move forward through the wave function along a particular trajectory. Others, like physicist Julian Barber, claim the wave function represents a timeless reality. All moments exist simultaneously in configuration space. Our perception of time flowing is an artifact of how our consciousness samples the wave function. Past, present, and future are all equally real, spread out across the landscape of quantum possibility. Either way, the universal wave function implies something staggering. Every version of history that could have happened does happen somewhere in the vast space of quantum outcomes. Your life contains countless branches where you made different choices, experienced different events, became a different person. They are all unfolding right now in parallel streams of existence. 2 particles meet in the void. Their wave functions overlap. In that instant, something profound occurs. Before the meeting, you could describe each particle independently. Particle A had its own wave function. Particle B had its own wave function. Simple. Separate. After they interact, separation becomes impossible. A single combined wave function now describes both particles together. This is quantum entanglement. Once entangled, the particles share a quantum state even if you move them to opposite sides of the galaxy. Measure a property of particle A, and you instantly gain knowledge about particle B. The correlation appears faster than light could travel between them. Einstein found this disturbing enough to call it spooky action at a distance. He proposed that hidden variables must exist, carrying information between the particles through normal means. John Bell proved in 1964 that hidden variables cannot explain entanglement. He derived inequalities that any hidden variable theory must satisfy. Experiments violate those inequalities. The particles really do share information instantaneously. No signal passes between them because they are not separate entities. They are two parts of one quantum system. In the many worlds interpretation, entanglement is the mechanism that creates new branches. When your brain processes information, electrons in your neurons interact with each other. These interactions entangle the electrons. The universal wave function splits. One branch contains neurons in state A, another branch contains neurons in state B. You split into versions, experiencing different thoughts. This branching happens constantly at every level. Air molecules in the room around you collide with each other roughly 1 billion times per second. Each collision entangles the molecules. Each entanglement splits reality. Photons from the device you are using strike your retina at a rate of trillions per second. Each photon creates entanglement and spawns branches where you saw slightly different patterns of light. The number of branches grows exponentially. Start with one universe. A single entanglement creates 2 branches. Another entanglement creates 4 branches. After just 100 entanglements, you have more branches than atoms in the visible universe. After 1,000 entanglements, the number of branches exceeds anything we can meaningfully describe with familiar notation. How many branches exist right now? Nobody knows. The mathematics of quantum mechanics does not specify whether the number is finite or infinite. Some physicists argue the number must be infinite because the universe contains continuous variables like position and momentum. Others suggest the number might be large but finite if space and time are fundamentally discrete at the Planck scale. What we do know is the number is enormous. David Deutsch put it bluntly. The number of parallel worlds is not 5, it is not a million. It is vastly, incomprehensibly larger than human intuition can grasp. And it grows every microsecond as more particles interact and entangle. Each branch is fully real. Each contains observers like you. Each evolves according to the same physical laws. The branches cannot communicate with each other directly. Once splitting occurs, the branches decohere and become causally isolated. Information cannot pass between them through normal means. Yet some physicists now argue that brief moments of interference between nearby branches might be possible. If true, this could change everything we thought we knew about the isolation of parallel worlds. For nearly a century, physicists argued about what happens when you measure a quantum system. Before measurement, the system exists in superposition. After measurement, you see a definite outcome. The wave function appears to collapse from many possibilities to one actuality. This sudden change violates the Schrödinger equation, which describes smooth, continuous evolution. So when and how does collapse occur? Niels Bohr, one of the founders of quantum mechanics, claimed measurement is fundamentally different from ordinary physical processes. A quantum system obeys one set of rules. Measuring devices obey another set. The boundary between quantum and classical is where collapse happens. This view, called the Copenhagen interpretation, dominated physics for decades. The problem is that measuring devices are made of atoms. Atoms obey quantum mechanics. So do the electrons in wires that carry measurement signals. So do the neurons in your brain that process those signals. Where exactly does the quantum world end and the classical world begin? Bohr never provided a clear answer. He suggested consciousness might play a role, which opened the door to mysticism that many physicists found uncomfortable. Other interpretations tried to solve the problem differently. The pilot wave theory, developed by Louis de Broglie and David Bohm, proposes that particles have definite positions at all times. They are guided by a hidden wave field that is real but invisible. Measurement reveals the position that was always there. This saves definite outcomes but requires adding new elements to physics. It also makes the theory non-local in disturbing ways. Change something here, and hidden waves everywhere must respond instantly. The many worlds interpretation eliminates the measurement problem entirely by denying that collapse happens. The wave function never reduces from multiple possibilities to one outcome. Instead, the observer becomes part of the system. Before you measure an electron's position, you exist in superposition too. Your brain has not yet processed the measurement result. After you look, one version of you sees the electron here, another version sees it there. Both versions are real. This seems to multiply mysteries rather than solve them. How can you exist in multiple states? Why do you only experience one outcome? The answer lies in decoherence. Your brain is made of roughly 86 billion neurons. Each neuron contains trillions of atoms. These atoms interact constantly with each other and with the environment. The interactions create entanglement so rapidly that different versions of you become isolated from each other in microseconds. Once decoherence occurs, the branches cannot interfere. They evolve independently. You in this branch have no way to access memories or experiences from other branches. It is not that they do not exist. They do. You just cannot perceive them because quantum interference has been suppressed. Think about how this changes the nature of observation. Measurement does not collapse reality. It entangles the observer with what is being measured. The universe does not care whether the observer is conscious. A simple photodetector will cause branching just as effectively as a human eye. Consciousness is not required for branching. It is just one type of physical system that becomes entangled with others. This resolves the measurement problem by showing there never was a problem. The equations of quantum mechanics already describe everything, including observers and measurements. No additional rules or assumptions are needed. Neurons in your brain fire through electrochemical processes that ultimately depend on quantum events. An ion channel opens when specific molecules change shape. That shape change involves electrons moving between different energy levels. Those electrons obey quantum mechanics. They exist in superposition before the interaction occurs. When the channel opens, the neuron fires. When it remains closed, the neuron stays silent. Both outcomes are real in different branches. This does not mean quantum mechanics controls your thoughts in some mystical way. Classical physics describes most brain function adequately. Neurons are large enough that decoherence happens almost instantly. Superposition cannot survive long enough to produce quantum effects at the level of thinking or decision-making. Your choices emerge from classical neuronal activity, not quantum uncertainty. But here is what matters for parallel universes. Even though quantum effects decohere quickly in warm, wet brains, the branching still occurs. Every quantum event in every neuron splits reality. One branch contains a neuron that fired, another contains a neuron that stayed silent. These tiny differences usually have no significant impact. Neurons fire or fail based on countless inputs. One quantum fluctuation rarely changes the outcome. Sometimes, though, a quantum event occurs at a critical moment. A neuron sits precisely at threshold. It will fire if it receives one more input. That input depends on whether a particular molecule is in state A or state B. Quantum mechanics says the molecule exists in superposition of both states. The universal wave function branches. In one branch, the neuron fires and you think thought X. In another branch, the neuron stays silent and you think thought Y. Scale this across billions of neurons processing information continuously. The number of branches where your thoughts differ from this moment grows quickly. Most branches contain versions of you thinking nearly identical thoughts. You are reading this sentence and processing its meaning in the vast majority of branches. But in some branches, a distraction caught your attention. In others, you misread a word. In rare branches, A quantum fluctuation caused a significantly different neural cascade, and you are thinking about something completely different right now. Extend this across your lifetime. Every moment contains billions of quantum events in your nervous system. Most produce branches that rejoin quickly. The versions of you converge back to similar states because classical physics dominates at macroscopic scales. But occasionally, quantum events occur at critical decision points. You hesitate before speaking. You reconsider a choice. A memory surfaces or stays buried. These moments generate branches that diverge substantially. Over decades, the divergence compounds. Versions of you made different friends, pursued different careers, live in different cities. All these versions experience themselves as the only version. Each one has continuous memories stretching back to childhood. Each one feels like the real you. From inside any particular branch, the others are invisible. Does this mean you lack continuity of identity? Not quite. The you reading these words right now is a real person with real experiences. Your subjective sense of self is not an illusion. It is just incomplete. You are one thread in a vast tapestry of related selves, all experiencing their own version of reality. Somewhere in the quantum multiverse, another version of you just finished reading this and decided they cannot accept it. In 1935, Erwin Schrödinger imagined a thought experiment that would haunt physics forever. Place a cat inside a sealed box. Add a radioactive atom that has a 50% chance of decaying within 1 hour. Connect the atom to a device that releases poison if decay occurs. Close the box and wait. According to quantum mechanics, the atom exists in superposition of decayed and not decayed states. The poison release mechanism becomes entangled with the atom. The cat becomes entangled with the poison. Before you open the box, the entire system exists in superposition. The cat is neither alive nor dead. It is both alive and dead simultaneously. Schrödinger intended this as a reductio ad absurdum. He thought it proved quantum mechanics must be incomplete because cats obviously cannot be both alive and dead. But quantum mechanics is not incomplete. The math works perfectly. Experiments confirm its predictions at every scale we can test. The issue is not with the physics. The issue is with our intuition. We assume opening the box forces the cat to become either alive or dead. We assume one outcome is real and the other vanishes. The many worlds interpretation says both outcomes are real. When you open the box, you do not collapse the cat's wave function. You become entangled with the cat. The universe splits. In one branch, you find a living cat. You feel relief. You pet the cat and give it food. In another branch, you find a dead cat. You feel sadness. You deal with the body. Both versions of you exist. Both versions of the cat exist. Both versions continue their separate lives in isolated branches of reality. From your perspective inside one branch, the cat appears to have been definitely alive or definitely dead the whole time. Your memories make it seem like the outcome was always determined. But that is because your memories themselves branched when you opened the box. The version of you who found a living cat has memories consistent with a living cat. The version who found a dead cat has memories consistent with a dead cat. Schrödinger himself later reconsidered his thought experiment. In 1952, he gave a lecture in Dublin where he suggested something remarkable. He proposed that both outcomes really do happen. They just happen in separate realities that do not interact. He cautioned his audience that this might sound lunatic. Then he defended it as the most straightforward reading of the quantum equations. The cat experiment reveals something crucial about measurements. The cat is itself a measuring device. When the radioactive atom decays, or does not decay, the cat measures this fact by dying or surviving. The cat does not need consciousness or intelligence to count as a measurement. Physical interaction is all that matters. The moment the atom decays, it entangles with the poison mechanism. The moment the poison releases, it entangles with the cat. Branching happens at each step. Consciousness enters later when you open the box. You add yourself to the entangled system You do not cause the branching. You join branching that already occurred. The cat was already in superposition of alive and dead states, with both states fully realized in different branches. You just chose which branch to experience. In the first tiny fraction of a second after the Big Bang, something extraordinary happened. Space itself expanded exponentially. The universe doubled in size, then doubled again, then doubled again. This happened so rapidly that in less than 1/1,000,000,000 of a trillionth of a trillionth of a second, a region smaller than an atom inflated to larger than the observable universe we see today. Physicists call this period cosmic inflation. Alan Guth proposed inflation in 1980 to solve several problems with the Big Bang model. Why does the universe look so smooth and uniform on large scales? Why is space flat rather than curved? Inflation explains both. By expanding space faster than light, inflation smooths out irregularities and flattens curvature. Observations of the cosmic microwave background confirm these predictions with remarkable precision. But inflation comes with a consequence Guth recognized immediately. Once inflation starts in one region, it probably never completely stops everywhere. Quantum fluctuations in the inflating field create bubbles where inflation ends and normal expansion begins. Our observable universe exists inside one such bubble. But outside our bubble, space continues inflating. And that inflating space spawns more bubbles. Each bubble becomes its own universe with its own Big Bang. This is eternal inflation. The process never ends globally, even though it ends locally inside bubbles. New universes form constantly. They expand and fill with galaxies and stars. Some might have the same physical constants as ours. Others might have different values for the strength of gravity, the charge of electrons, the mass of quarks. Most bubble universes would have constants that prevent structure formation. No stars, no planets, no complexity. A few lucky bubbles, like ours, get parameters that allow interesting things to happen. Andre Linde at Stanford University refined this picture. He showed that eternal inflation is not just possible, but almost inevitable, given what we know about quantum fields. Even if inflation stops in most regions, quantum fluctuations will always restart it somewhere. The multiverse of bubble universes is the natural outcome of our best theory of the early universe. How big is this multiverse? Incomprehensibly vast. Each bubble universe can be infinite in size, and there are likely infinite numbers of bubbles. Cosmologists sometimes describe this as a level 1 multiverse, distinct from the quantum many-worlds multiverse. But the two types of multiverse might be related. Some theories suggest eternal inflation happens differently in different branches of the quantum wave function. The bubbles are separated by eternally inflating space. That space expands faster than light. No signal or particle can cross from one bubble to another once they form. The bubbles are causally disconnected. You cannot travel to other bubble universes or communicate with them through any known means. Almost. There is one exception. If two bubbles form close enough together during inflation, they might collide before inflation separates them. The collision would leave marks on both bubbles. From inside one bubble, looking at the cosmic microwave background, you might see a circular pattern where the collision occurred. Something like a bruise in the sky. Something like the cold spot astronomers discovered. If the cold spot is a collision signature, it would be our first evidence that eternal inflation really produces multiple universes, and it would mean our universe literally touched another reality. Change the strength of gravity by 1 part in 10 to the power of 34, and stars cannot form. Make the electromagnetic force slightly stronger, and atomic nuclei cannot hold together. Adjust the mass of the electron by a small amount, and chemistry becomes impossible. The constants of nature appear precisely calibrated to allow complex structures like galaxies, stars, planets, and life. Physicists call this fine-tuning. It is not that the constants are special numbers with mathematical significance. They could have any value as far as the laws of physics are concerned. The mystery is why they happen to fall within the narrow ranges that permit structure formation. The probability seems vanishingly small if the constants are random. Some see design in this fine-tuning. If the universe appears constructed for life, perhaps something or someone constructed it that way. This is the anthropic principle in its strongest form. The universe must have properties compatible with observers, because otherwise there would be no observers to notice. Scientists generally resist this reasoning because it stops inquiry. Saying the universe is fine-tuned for life explains nothing about why the constants have their specific values. It just restates the observation as a conclusion. Most physicists look for physical mechanisms that could explain fine-tuning without invoking purpose or intent. The multiverse offers such a mechanism. If countless universes exist with different physical constants, then some will have the right values purely by chance. We find ourselves in one of those universes because we could not exist in the others. The apparent fine-tuning is a selection effect. We observe a life-permitting universe not because the universe was designed for life, but because we can only exist in universes where our kind of life is possible. Think about this using an analogy. Imagine a cosmic lottery where each universe is assigned random constants. Most tickets are losers. They produce universes too hot, too cold, too unstable, or too uniform to develop complexity. A tiny fraction of tickets win, creating universes that can host stars and planets and eventually observers. We hold a winning ticket not because winning is common, but because we could not be here to examine a losing ticket. The analogy breaks down because the number of universes is not like a fixed number of lottery tickets. Eternal inflation might create infinite bubble universes. The quantum many-worlds interpretation might generate infinite branches. In an infinite multiverse, every possible combination of constants occurs infinitely many times. Fine-tuning becomes not just likely, but inevitable. Some physicists dislike multiverse explanations for fine-tuning. They argue it abandons the scientific goal of prediction. If anything can happen somewhere in the multiverse, the theory loses explanatory power. Others respond that the multiverse is a prediction of inflation and quantum mechanics, not an assumption added to solve the fine-tuning problem. We follow the math where it leads, even if it leads to strange conclusions. The debate remains unresolved, but the stakes are clear. If the multiverse is real, then our universe is not special. The constants that allow our existence are accidents of cosmological geography. Somewhere, in the vast landscape of possible universes, conscious beings ask the same questions we ask and reach the same unsettling conclusions. They are just as surprised and perhaps just as frightened to realize they are not alone. Roger Penrose stands apart from most physicists on the question of parallel universes. He argues the many worlds interpretation fails because it ignores gravity. Quantum mechanics describes particles and fields successfully, but we lack a complete theory of quantum gravity. Penrose claims that gravity plays a crucial role in determining what is real and what remains merely possible. His argument centers on the relationship between mass and quantum superposition. Tiny particles like electrons have negligible gravitational fields. They can maintain superposition indefinitely in isolated systems. The universal wave function describes their state perfectly. But large objects create significant gravitational fields. Gravity curves space-time around them. Here is where things get interesting. If an object exists in superposition of two different positions, it creates two different gravitational fields. Those fields curve space-time in different ways. Now you have superposition not just of particle positions, but of space-time geometries. Penrose argues this is physically unstable. The universe cannot maintain two contradictory space-time curvatures for long. He proposes that gravity causes wave function collapse. When an object's superposition creates sufficiently different space-time geometries, the instability forces one geometry to become real and the others to vanish. This happens automatically through gravitational physics, no consciousness required. No special measurement process needed, just gravity doing what gravity does. The threshold for collapse depends on mass and duration. An electron can stay in superposition forever because its gravitational field is immeasurably tiny. A dust particle weighing 1 microgram might maintain superposition for 1 second before gravity collapses it. A cat-sized object collapses in microseconds or faster. The more massive the object, the quicker gravity forces it into a definite state. This would mean large-scale branching does not occur. The universe splits for quantum particles, but those splits heal rapidly when the particles interact with massive objects. Only one macroscopic reality exists. Many worlds is an approximation valid only at microscopic scales where gravity can be ignored. Most physicists remain skeptical of Penrose's objective collapse theory. The mathematics is not fully developed. Experimental tests are difficult because the predicted effects are subtle. You would need to put increasingly large objects in superposition and measure how long the superposition lasts. Current technology can barely create superposition of molecules. Objects massive enough to test gravitational collapse lie far beyond our experimental reach. More fundamentally, Penrose's theory requires modifying quantum mechanics. It adds new physics beyond the Schrödinger equation. Many physicists prefer interpretations that stick with standard quantum mechanics rather than proposing new collapse mechanisms. The many-worlds interpretation requires no changes to the underlying physics. It just takes the equations seriously. Yet Penrose makes a valid point. We do not understand quantum gravity. General relativity and quantum mechanics are incompatible in their current forms. Any complete theory must merge them somehow. Perhaps that merger will reveal that gravity prevents infinite branching. Perhaps the universe has a mechanism to select one outcome from many possibilities. Or perhaps gravity itself exists in superposition across different branches. Maybe there is no universal space-time geometry, but rather different geometries in different worlds. The equations of general relativity might describe not one curved space-time, but infinitely many parallel spacetimes evolving independently. Until we have a working theory of quantum gravity, we cannot know which picture is correct. David Deutsch designed quantum computers not to solve practical problems, but to prove the many worlds interpretation is real. He reasoned that if parallel universes exist, we should be able to harness their computational power. A quantum computer with 300 quantum bits could perform calculations involving more states than there are atoms in the observable universe. Where does that processing power come from if only one universe exists? A quantum bit, or qubit, can be 0 and 1 simultaneously. 2 qubits can represent 4 states at once. 3 qubits represent 8 states. The number of states grows exponentially. Each qubit doubles the number of states the system can represent. A 300-qubit computer represents 2 to the power of 300 states simultaneously. That number exceeds 10 to the power of 90. Classical computers process one calculation at a time. To solve certain problems, they must try every possible answer sequentially. Quantum computers process all possible answers simultaneously through superposition. When the computation finishes, you measure the result and get the answer. The computer leveraged quantum parallelism to search through vast solution spaces that would take classical computers billions of years to explore. But here is the remarkable part. While the computation runs, the qubits exist in superposition of all possible states. The quantum computer is literally performing calculations in parallel across all those states. In the many worlds interpretation, each state exists in a different branch of reality. The quantum computer spawns countless parallel universes, performs a different calculation in each one, then brings the results back together through quantum interference to produce the final answer in this branch. Deutsch argues this is evidence that parallel worlds are real. How else can 300 qubits process 2 to the power of 300 states simultaneously? The computer must be borrowing computational resources from parallel universes. Each universe performs part of the calculation. The results interfere to give us the answer we observe. Other interpretations of quantum mechanics deny this. The Copenhagen interpretation says the qubits do not have definite states until measurement. The computation happens in some abstract quantum realm that is not quite real. Pilot wave theory says there is a single actual state, but it is guided by a hidden wave that explores all possibilities. Deutsch dismisses these alternatives as unsatisfying. The many worlds interpretation treats the quantum computer straightforwardly. It performs parallel calculations in parallel worlds. The interference between worlds is what makes quantum computing more powerful than classical computing. If parallel worlds did not exist, quantum computers would have no advantage. Quantum computers remain experimental technology. The largest current systems have around 1,000 qubits, but cannot maintain quantum superposition for long enough to solve interesting problems. Errors accumulate rapidly. Decoherence destroys the quantum state. Building practical quantum computers requires solving immense engineering challenges. Yet progress continues. Companies and research labs worldwide are racing to build quantum computers that can solve real problems. When they succeed, we will have devices that demonstrably leverage quantum parallelism to outperform any classical computer. And according to Deutsch, we will have proof sitting on our desks that parallel universes are not speculation. They will be technology we use every day to solve problems impossible in a single universe alone. Light travels at 300,000 kilometers per second. Nothing can move faster through space. This speed limit, built into the structure of space-time itself, creates an invisible barrier around us. Light from distant galaxies took billions of years to reach Earth. We see those galaxies as they appeared in the distant past. The farther we look, the further back in time we see. But there is a limit to how far we can see. The universe is 13.8 billion years old. Light has only had 13.8 billion years to travel. Objects more than 13.8 billion light years away have not had time to send light to us yet. Their light is still in transit. This creates the cosmic horizon, the boundary of the observable universe. The actual distance to that horizon is larger than 13.8 billion light-years because space itself expands. While light travels toward us, space stretches. The current size of the observable universe is roughly 93 billion light-years across. Everything beyond that horizon is invisible to us. Not because something blocks our view, simply because not enough time has passed for light to arrive from there. Now think about bubble universes from eternal inflation. Each bubble forms in a sea of exponentially expanding space. The space between bubbles inflates faster than light. Not faster than light moves through space, which is impossible. Rather, space itself expands so rapidly that the distance between bubbles grows faster than light could cross that distance. This means bubble universes become causally disconnected from each other. Light from one bubble cannot reach another bubble. Signals cannot pass between them. Information cannot flow across the inflating barrier. Each bubble becomes its own isolated island of space and time. The inhabitants of one bubble cannot know about other bubbles. They cannot visit them. They cannot communicate with them. The same principle applies to the quantum many worlds. Different branches of the wave function decohere from each other. They stop interfering. They evolve independently. The branches exist in quantum configuration space, not in physical three-dimensional space. But the isolation is just as complete. You cannot send a message to another branch. You cannot travel there. You cannot look across the divide to see what versions of you are doing in other worlds. This is why we cannot visit parallel universes even if they exist. They are not distant places we could reach by traveling far enough. They are separate realities, isolated by the fundamental structure of physics. The isolation might be guaranteed by the speed of light in the case of bubble universes. It might be guaranteed by decoherence in the case of quantum branches. Either way, the barriers appear absolute. Some physicists speculate about exceptions. Perhaps quantum tunneling could connect different bubbles if they form close enough together. Perhaps brief moments of recoherence could allow interference between quantum branches under special conditions. Perhaps wormholes or other exotic space-time structures could bridge the gaps. These ideas remain highly speculative. For now, parallel universes, if they exist, remain forever separate from ours. But what if the cold spot proves they sometimes collide? Ruari Mackenzie, a graduate student at Durham University, spent months analyzing data from two major galaxy surveys. His goal seemed straightforward: confirm the Eridanus supervoid existed and explained the mysterious cold spot in the cosmic microwave background. Previous research in 2015 claimed to find this void. Mackenzie aimed to verify it using newer, more detailed observations. He combined data from the Anglo-Australian telescope with the Gamma survey, which had mapped thousands of galaxies with precise distance measurements. The technique involved spectroscopy. Light from each galaxy contains signatures from different chemical elements. As space expands, these signatures shift to longer wavelengths. The amount of shift reveals how far away the galaxy sits. By mapping galaxy positions in 3 dimensions, astronomers can identify voids and clusters. The cold spot spans 5 degrees on the sky. If a giant void caused it through the integrated Sachs-Wolf effect, the void would need to be enormous. Estimates suggested 500 million to 1 billion light-years across, a structure that large should show up clearly in galaxy surveys. The region in front of the cold spot should have significantly fewer galaxies than surrounding areas. Mackenzie ran the analysis. He compared galaxy density around the cold spot to galaxy density in control regions elsewhere in the sky. The results surprised him. The cold spot region looked normal. Galaxy distribution there matched galaxy distribution everywhere else within measurement uncertainties. No giant void appeared in the data. He checked his calculations. He tried different statistical methods. He expanded the sample size. He looked at different distance ranges. Every test gave the same answer. Whatever the supervoid hypothesis predicted should be, there was not there. The 2015 study that claimed to find the void could not be replicated with better data. This created a problem. The cold spot is real. Planck's satellite confirmed its existence. Multiple independent analyses agreed on its properties. Something causes that region of the cosmic microwave background to be significantly colder than predictions allow. If no void causes it, then what does? Mackenzie and his advisor, Tom Shanks, submitted their results to monthly notices of the Royal Astronomical Society in 2017. They acknowledged the unsettling implications. Standard cosmology struggles to explain such a large cold region. The probability of random fluctuations producing the cold spot sits around 1 to 2%, possible but unlikely, and uniqueness matters. Other large cold spots should exist if this one formed by chance. None have been found. The paper mentioned exotic alternatives, cosmic textures, topological defects from phase transitions in the early universe, collisions with other bubble universes during inflation. Each explanation requires physics beyond the standard model of cosmology. Each faces skepticism from the scientific community. Yet ruling out conventional explanations makes exotic alternatives worth considering. Shanks stated in a press release that if further analysis confirms no supervoid exists, then bubble collision becomes the next most reasonable hypothesis. This does not prove the cold spot is evidence of parallel universes. It means parallel universes move from speculative fantasy to testable scientific hypothesis. That shift matters. Science progresses by eliminating possibilities until only the truth remains, however strange that truth might be. Laura Massini Houghton at the University of North Carolina made a striking proposal. The cold spot is not random chance. It is not a supervoid. It is a scar from when our universe collided with another universe before cosmic inflation separated them. The collision happened 13.8 billion years ago, a tiny fraction of a second after the Big Bang. We are seeing the consequences now written across the oldest light in the cosmos. Her argument builds on eternal inflation theory. Quantum fluctuations in the inflation field create bubble universes constantly. Most bubbles form far apart and never interact, but sometimes two bubbles nucleate close enough that they touch before inflation pushes them apart. When bubbles collide, they release energy at their boundary. This energy propagates through both bubbles as a spherical wave. From inside one bubble, we would see the collision signature as a circular pattern in the cosmic microwave background. The pattern size depends on when and where the collision occurred relative to our position in space and time. Mathematical models predict specific temperature profiles. The cold spot matches these predictions reasonably well, though not perfectly. Mersini-Houghton goes further. She claims quantum entanglement connects our universe to other universes that formed during the same inflationary epoch. Before inflation separated the bubbles, they shared quantum states. The bubbles became entangled. Even after spatial separation made them causally disconnected, quantum correlations persisted. This is controversial. Most physicists argue entanglement cannot survive across separate universe bubbles. Inflation expands space so rapidly it should break any quantum connections. The bubbles become isolated systems with no way to influence each other. Entanglement requires the ability to verify correlations through measurements, which becomes impossible when no signal can travel between universes. Mersini-Houghton counters that the entanglement formed before inflation completed. The quantum state of the multiverse includes correlations between bubbles as a permanent feature. We cannot verify these correlations directly because we cannot communicate with other bubbles, but the correlations affect observable properties like the cosmic microwave background temperature distribution. The cold spot could be evidence of quantum entanglement between universes. Her ideas attract skepticism from the mainstream physics community. Critics point out that the cold spot could still be a statistical fluke. 1 to 2% probability events happen. Unusual features in cosmological data are not automatically evidence of new physics. Extraordinary claims require extraordinary evidence. A single anomalous cold spot is not enough to confirm the multiverse. Mersini-Houghton acknowledges the uncertainty. She emphasizes that her proposal is testable. Future observations with higher resolution could reveal additional structure in the cold spot. If it is a collision signature, it should have specific geometric properties that differ from random fluctuations. Upcoming cosmic microwave background experiments might provide the data needed to distinguish between competing explanations. For now, her work represents the frontier where speculation meets science. The cold spot might be nothing remarkable, or it might be our first glimpse of another reality that touched ours at the beginning of time. The evidence remains ambiguous. The debate continues. What matters is that the question has moved from philosophy to physics. Scientists are designing experiments to test whether other universes exist. The answer could arrive within our lifetimes. Max Tegmark at MIT proposes something radical. If a mathematical structure is consistent and well-defined, it exists, not as abstract equations on paper, as physical reality. Somewhere in the vast landscape of possible universes, every mathematical structure that can exist does exist. He calls this the mathematical universe hypothesis. This goes beyond the multiverse theories we have discussed. Quantum many worlds suggests different branches where particles have different positions or momenta. Eternal inflation suggests different bubbles where physical constants have different values. Tegmark's Level 4 multiverse suggests entirely different mathematical structures. Universes where time has 2 dimensions instead of 1. Universes where space has 17 dimensions instead of 3. Universes governed by mathematical laws we cannot even imagine. Why would all mathematical structures exist as physical realities? Tegmark argues it follows from a principle of democracy. If some mathematical structures correspond to physical universes, why only certain structures? What makes our mathematical laws special? Unless we invoke some external selector choosing which mathematics becomes real, the simplest assumption is that all consistent mathematics generates reality. This sounds like wild speculation, but Tegmark points out our own universe appears to be purely mathematical in nature. Every physical law can be expressed as equations. Every property of matter and energy corresponds to mathematical structures. Space and time form a mathematical geometry. Quantum states live in abstract vector spaces. The universe computes its own evolution according to mathematical rules. Perhaps reality is mathematics. Perhaps the physical world is not described by mathematics, but rather is mathematics. We exist as patterns within a vast mathematical structure. Consciousness emerges from sufficiently complex mathematical processes. When we discover mathematical truths through physics, we are discovering facts about the structure we inhabit. If this is correct, then asking why our universe has its particular mathematical structure is like asking why the number 7 has its particular properties. 7 is not chosen from among possible numbers. 7 exists necessarily as part of mathematical reality. Our universe exists necessarily as one structure in the space of all possible structures. Critics argue this is untestable. How could we ever verify that universes with completely different mathematical laws exist? We are trapped inside our mathematical structure. We cannot step outside to observe others. The hypothesis makes no predictions we could check. It becomes philosophy rather than physics. Tegmark responds that the hypothesis does make predictions. It predicts we should find ourselves in a typical universe among all universes that can support observers. Most mathematical structures probably cannot generate complexity. Most would be too simple or too chaotic to evolve life. We should expect to inhabit a universe from the subset that allows structure formation. And indeed, our universe appears surprisingly well suited for complexity while having no obvious reason to be that way. The debate remains unresolved, but the mathematical universe hypothesis represents the most extreme version of the multiverse idea. Not just many universes with different properties, infinite universes with every possible mathematical structure. If Tegmark is right, then reality is far vaster and stranger than even the wildest speculation suggests. David Deutsch made a startling claim. Parallel universes do not remain completely isolated. Brief moments of interference occur when quantum processes force previously identical universes to become distinct. During the double-slit experiment, he argues, temporary interaction between worlds produces the interference pattern we observe. Consider what happens when an electron approaches two slits. Before reaching the barrier, one electron exists in one universe. Then superposition creates branching. In some branches, the electron heads towards slit A. In others, it moves towards slit B. The branches become distinct. They contain slightly different configurations of reality, but the branches are not yet completely separated. They remain close enough in configuration space that quantum interference can occur between them. The electron passing through slit A in one branch interacts with the electron passing through slit B in another branch. This interaction creates the interference pattern. When the electron hits the detection screen, the branches fully separate. Interference stops. Each branch contains a screen with an electron impact at a specific location. From inside any single branch, you see one electron making one dot. But the pattern that emerges after many electrons reveals the interference that occurred between branches. The pattern proves the electron interacted with something. Yet no other electron was present in your branch. The interaction must have occurred with the electron in parallel branches. Deutsch argues this explains why quantum mechanics works at all. Classical physics describes one world. Quantum mechanics describes the interference between many worlds. The wave function is not a mathematical tool. It is a real structure spanning multiple realities. When we calculate using the wave function, we are accounting for how worlds interact before they separate completely. Most physicists remain skeptical of this interpretation. They accept the many worlds picture, but deny that interference between worlds is the right way to understand quantum experiments. The standard view says interference happens within one branch before measurement occurs. Only after measurement do branches split and become isolated. No interaction between distinct branches is needed. Yet Deutsch's interpretation has an appealing feature. It explains quantum computing naturally. A quantum computer maintains superposition across multiple computational paths. Those paths exist in different branches. The final result depends on interference between branches before measurement collapses the superposition. The computer leverages temporary interference between parallel worlds to solve problems. Some recent proposals go further. They suggest we might engineer situations where recoherence occurs, allowing branches that have separated to merge back together. This would require exquisite control over quantum systems. Any interaction with the environment causes decoherence and prevents merging. But in principle, quantum mechanics allows previously separated branches to rejoin if you can reverse all the entanglements that split them. If this becomes possible, we might achieve something remarkable. Brief communication between parallel worlds. Not travel, not permanent contact. Just fleeting moments where information passes between branches before they diverge again. This remains far beyond current technology. The theoretical possibility exists. Somewhere in quantum configuration space, parallel versions of you might be working on the same problem you face now. Your thoughts might interfere with theirs in ways too subtle to notice consciously, but the interference is real. How often does the universe branch? Every quantum interaction creates new worlds, but quantum interactions happen constantly everywhere. Calculating the total branching rate requires understanding how many quantum events occur across the entire cosmos. Start small. A single atom contains electrons orbiting a nucleus. Those electrons transition between energy levels. Each transition is a quantum event. Multiply by roughly 10 to the power of 80 atoms in the observable universe. Even if each atom only undergoes one transition per second, that is 10 to the power of 80 branching events per second, the actual rate is far higher. Photons from stars constantly hit atoms in interstellar gas. Cosmic rays bombard planetary atmospheres. Radioactive decay occurs in rocks. Neutrinos pass through matter and occasionally interact. Each event creates entanglement and spawns branches. Sean Carroll estimates the branching rate in our local vicinity alone exceeds billions of events per second. Scale this across the observable universe. Every galaxy contains hundreds of billions of stars. Each star emits quadrillions of photons per second. Each photon that interacts with matter creates branching. The total number quickly becomes incomprehensible. The universe might split more times in 1 second than there are atoms in the observable cosmos. Does this mean the number of branches is infinite? Not necessarily. If the universe is finite in size and contains a finite number of particles, then the branching rate is large but finite. Over the 13.8 billion year lifetime of the universe, the total number of branches could be enormous yet countable. Some cosmologists argue for this view. Others claim the number must be infinite. If space is infinite, then infinitely many quantum events happen simultaneously across the cosmos. Each second adds infinite new branches to the already infinite collection. The multiverse becomes not just large, but infinite in an uncountable sense, infinity upon infinity. The mathematics of quantum mechanics does not specify which scenario is correct. The wave function describes probabilities for different outcomes. It does not count how many branches exist or tell us whether the number is finite or infinite. This remains an open question in physics. What about the future? Does branching continue forever or eventually stop? As long as quantum events occur, branching continues. But the universe is expanding and cooling. Eventually, stars will burn out, galaxies will disperse, black holes will evaporate through Hawking radiation. In the far future, trillions of years from now, the universe might reach a state where quantum events become rare. Yet even an almost empty universe will have quantum fluctuations in whatever fields pervade space. Virtual particles will appear and vanish. The vacuum itself undergoes quantum processes. As long as anything exists, branching probably continues. The multiverse might grow without bound forever, adding new worlds to itself eternally. Every moment you exist, reality multiplies. Every thought you think creates branches. Every decision generates parallel lives. The you reading this sentence is already just one among countless versions that have diverged in the microseconds since you started reading. The branching never stops. The multiplication never ends. Galaxies rush away from each other. Space expands everywhere simultaneously, but the expansion is accelerating. Gravity should slow the expansion over time as galaxies pull on each other. Instead, some mysterious force pushes them apart faster and faster. Physicists call this dark energy. Dark energy constitutes roughly 68% of all energy in the universe, yet we have no idea what it is. The leading explanation suggests space itself has energy. Every cubic meter of vacuum contains a tiny amount of intrinsic energy that drives expansion. This is the cosmological constant that Einstein introduced and later called his greatest blunder. The problem is the predicted value. Quantum field theory calculates how much vacuum energy should exist based on virtual particles appearing and vanishing. The calculation gives an answer roughly 10 to the power of 120 times larger than observations allow. This is the worst prediction in the history of physics. Something is profoundly wrong with our understanding. Some physicists propose the multiverse might explain this discrepancy. If different bubble universes have different vacuum energy values, then most universes would have energy densities far from what we observe. In universes with very large positive vacuum energy, space expands so fast that matter never clumps into galaxies or stars. In universes with large negative vacuum energy, space collapses back on itself too quickly for structure to form. Only universes with vacuum energy close to zero allow complexity. We find ourselves in such a universe because observers cannot exist in the others. The multiverse plus anthropic selection explains why the cosmological constant seems fine-tuned. It is not fine-tuned. We just happen to live in one of the rare bubbles where the value permits our existence. But some researchers propose something more radical. What if dark energy represents leakage from other universes? Imagine parallel worlds stacked in extra dimensions. If gravity can propagate through those extra dimensions, then massive objects in nearby parallel universes might exert gravitational pull on our universe. From our perspective, this would appear as an extra force pushing things apart or pulling them together. The mathematics is speculative. Brain cosmology models suggest our universe is a three-dimensional membrane floating in higher dimensional space. Other membranes exist nearby. Gravity operates in all dimensions, creating connections between branes. Dark energy might be gravity leaking from parallel branes into ours. This hypothesis makes testable predictions. If dark energy comes from nearby branes, its strength should vary slightly over cosmic time or across different regions of space. Future observations with more sensitive instruments could detect these variations. Standard vacuum energy should be perfectly uniform. Brain leakage would show patterns. No such patterns have been found yet. Measurements suggest dark energy appears constant within current error margins, but the data improves continually. Upcoming surveys will measure the expansion history with unprecedented precision. If variations appear, we might discover that dark energy has been our first indirect contact with parallel universes all along. The force pushing galaxies apart might be gravity from countless other worlds pressing against ours. String theory requires extra dimensions beyond the 3 spatial dimensions we perceive. Early versions needed 9 spatial dimensions plus 1 time dimension for the mathematics to work consistently. These extra dimensions must be compactified, curled up so small we cannot detect them directly. Every point in our familiar 3-dimensional space actually extends into 6 additional microscopic dimensions. But some string theorists propose the extra dimensions might be large rather than small. We live on a 3-dimensional surface, a brain, embedded in higher dimensional space. The brain is our entire observable universe. We cannot move off the brain or perceive the extra dimensions directly because all matter and radiation are confined to the brain. Only gravity can escape into the bulk, the higher dimensional space surrounding all brains. This brain cosmology suggests multiple brains exist floating in the bulk. Each brain is a separate 3-dimensional universe. The brains might be parallel, stacked like sheets of paper, or they might be positioned at angles to each other. The distance between brains through the bulk could be microscopic, even though the brains themselves are vast. What happens if brains collide? Neil Turok and Paul Steinhardt developed the ekpyrotic model to answer this question. They proposed that our Big Bang was actually the collision between 2 brains. Before the collision, both brains existed in a cold, empty state. The collision released enormous energy, heating both brains and filling them with radiation. This is what we call the Big Bang. After colliding, the brains bounce apart. They move through the bulk, cool down, and eventually collide again. The cycle repeats eternally. Each collision creates a new Big Bang. The universe goes through infinite cycles of collision, expansion, cooling, contraction, and collision again. Time has no beginning or end in this model. Brain cosmology makes specific predictions about the cosmic microwave background. The pattern of temperature fluctuations should differ slightly from standard inflation models. Gravitational waves from the Big Bang should have different properties. So far, observations have not found clear evidence for or against the ekpyrotic model. The differences are subtle and require more precise measurements to detect. But here is what matters for parallel universes. If we live on a brain, then other brains exist nearby, in extra dimensions. Those brains are separate universes. They have their own space, time, matter, and energy. The only connection is gravity leaking through the bulk. Brain collisions would leave marks. The collision releases energy primarily where the brains touch. From our perspective on one brain, this creates a localized hot or cold spot in the cosmic microwave background. The spot's size depends on the geometry of the collision and our position relative to the contact point. Some researchers argue the cold spot could be evidence of a brain collision rather than a bubble collision. The mathematics differs slightly, but the observable consequences are similar. Both predict circular anomalies in the ancient light from the early universe. Multiple types of parallel universe theories converge on the same prediction. They all suggest we should see scars in the sky. Scientists must be honest about uncertainty. The cold spot has roughly a 1 to 2% probability of occurring through random fluctuations in the standard Big Bang model, 1 in 50 to 1 in 100. These are not impossible odds. Unlikely events happen. Think about what 1% probability means. If you flip a fair coin 7 times, getting all heads has about a 1% chance. Surprising? Certainly. Evidence that the coin is rigged? Not necessarily. Run the experiment enough times, and 1% events occur regularly, with countless regions of the cosmic microwave background to examine. Finding one unusual spot should not shock us. This is the conservative position most cosmologists hold. The cold spot is weird. It deserves investigation. But jumping to parallel universe explanations is premature when a simple statistical fluke remains viable. Science demands we exhaust conventional explanations before invoking exotic alternatives. Tom Shanks from Durham University acknowledges this. His team ruled out the supervoid hypothesis, but that does not prove bubble collision occurred. He stated clearly that random chance remains on the table. The cold spot could be just an unusually large fluctuation that happened by accident. We got unlucky, or maybe lucky, depending on your perspective. Yet the 1% probability troubles some researchers. Yes, unlikely things happen, but science progresses by investigating anomalies. When observations do not match predictions, we learn something. Either our predictions are wrong, or we misunderstood something fundamental. The cold spot forces us to think carefully about both possibilities. Consider another issue. The cold spot is unique. No other comparably large cold regions appear in the cosmic microwave background. If 1% probability events occur randomly, we should see multiple cold spots. Instead, we see one. This uniqueness is itself unusual. The probability of seeing exactly one anomaly of this size, rather than 0 or several, becomes even smaller than 1%. Some statisticians argue we are asking the question wrong. The probability calculation assumes we specified in advance that we would look for a cold spot in this particular location with these exact properties, but we did not. We scanned the entire sky looking for anything unusual. When you search for any anomaly anywhere, the odds of finding something weird increase dramatically. This is the look elsewhere effect. How many different anomalies could we have noticed if they were present? Large hotspots, clusters of small cold regions, asymmetries, unusual geometric patterns. If we consider all possible anomalies we might have seen, then finding one specific anomaly becomes less surprising. The effective probability might be 10% or 20% rather than 1%. Matthew Kleban, who models bubble collisions, emphasizes that probability alone cannot answer the question. We need additional data. Future cosmic microwave background experiments will map the sky with higher resolution. They might reveal fine structure inside the cold spot that distinguishes random fluctuations from collision signatures, or they might find additional anomalies that clarify the situation. Until then, the 1% probability hangs over the debate like a cloud, just unlikely enough to fuel speculation, yet just likely enough to counsel caution. Scientists are designing experiments to find direct evidence of parallel universes. These experiments push the boundaries of current technology. Some might become feasible within decades. Others remain theoretical proposals for future generations to attempt. One approach targets the quantum many-worlds interpretation. If parallel branches can briefly interfere before fully decohering, we might detect that interference in carefully controlled experiments. The idea is to create a quantum system large enough to contain information, maintain it in superposition as long as possible, then measure whether interference patterns reveal properties of other branches. Quantum computers are candidates for such experiments. Current quantum computers struggle to maintain coherence for more than microseconds. Decoherence destroys the quantum state before interesting interference effects appear. But future quantum computers with thousands of stable qubits might stay coherent long enough for experiments. David Deutsch suggests a sufficiently sophisticated quantum computer could remember existing temporarily in multiple branches before decoherence separated them. Another approach looks for signatures of bubble collisions in upcoming cosmic surveys. The Simons Observatory and CMBS-4 project will map the cosmic microwave background with unprecedented precision. If the cold spot is a collision signature, these instruments should reveal predicted patterns in its structure. Multiple collision signatures might be found if we look carefully enough, or the data might rule out collision explanations entirely. Gravitational wave detectors offer another avenue. The Laser Interferometer Space Antenna, planned for launch in the 2030s, will measure gravitational waves from the early universe. Bubble collisions should produce specific gravitational wave signatures. These waves travel through space unchanged since the collision occurred. Detecting them would provide direct evidence that our universe touched another reality. Some physicists propose experiments to test whether dark energy comes from parallel branes. If extra dimensions exist, gravity should vary in strength at microscopic scales. Experiments searching for deviations from Newton's law of gravitation at sub-millimeter distances have found nothing yet, but more sensitive tests are planned. Finding unexpected forces at small scales would revolutionize physics and hint at the existence of nearby branes. Testing eternal inflation faces challenges. because most bubble universes are forever unreachable, but we can test whether inflation occurred at all. The pattern of density fluctuations in the cosmic microwave background matches inflation predictions precisely. Future measurements will either strengthen this match or reveal discrepancies. If inflation is confirmed beyond doubt, eternal inflation becomes much more plausible because it is difficult to start inflation without it continuing eternally in at least some regions. The most ambitious proposal involves using quantum entanglement across macroscopic distances. If particles on Earth can be entangled with particles in a carefully isolated system, and if the isolated system can be kept in superposition long enough, then measurements might reveal correlations that only make sense in a many-worlds framework. This requires technology far beyond current capabilities. Success would demonstrate that quantum effects scale up to observable levels. None of these experiments guarantee success. Parallel universes might exist yet remain fundamentally undetectable, or the experiments might fail for technical reasons unrelated to whether parallel worlds are real. But the attempt matters. For the first time in history, we have concrete ideas about how to test whether other realities exist. If every choice you make creates branches where you chose differently, does free will exist? In some branches, you decided to read this. In others, you stopped minutes ago. In still others, you never started. All versions are real. All versions experience themselves as making free choices. Yet the totality of branches includes every possible decision. This troubles many people. Free will seems to require that your choices shape reality. If reality includes all possible outcomes, regardless of what you choose, then your decisions appear meaningless. You cannot make anything happen or prevent anything from happening. Everything that could happen does happen somewhere. But this misunderstands what choice means in the many worlds interpretation. When you make a decision, you determine which branch you continue along. You cannot control the existence of other branches. You can control which branch contains you. This is free will in the sense that matters for subjective experience. Think about it from inside a single branch. You face a choice. You deliberate. You weigh options. You decide. Your decision shapes your future. The version of you in this branch experiences consequences of this specific choice. Other branches exist, yes, but you do not experience those branches. You experience this one. Your choices here are real and consequential for you. Determinism versus free will is an ancient philosophical debate. Many worlds does not resolve it so much as reframe it. In a deterministic universe with only one timeline, your choices might be predetermined by prior causes stretching back to the Big Bang. Many worlds says your choices are determined, but they determine which branch you occupy rather than which outcome occurs globally. Some philosophers argue this is enough to preserve moral responsibility. If your choices determine your experienced reality, then you bear responsibility for those choices. The fact that other versions made different choices does not excuse you from the consequences of your choices. Each version is accountable for the branch they create through their decisions. Others argue many worlds undermines moral significance. If every possible action occurs somewhere, then nothing is truly forbidden or required. Murder happens in some branches. Heroic sacrifice happens in others. The multiverse contains all possible moral outcomes. Why should we care about our particular branch when all branches exist equally? The response is that you experience your branch exclusively. You cannot perceive or access other branches. For you, your choices are the only ones that matter because they are the only ones you will experience consequences from. Moral philosophy applies to experienced reality, not to the totality of all possible realities. There is also a practical consideration. Even if all possibilities occur across branches, the Born rule says some branches have higher quantum weight than others. Your choices might influence which branches have greater weight. Making good choices could increase the proportion of branches where positive outcomes occur. This gives moral decisions real stakes, even in a many worlds framework. Perhaps the most important insight is this: the many worlds interpretation does not tell you what to do, it tells you what is. Whether you have free will depends on what free will means. If it means having exclusive control over which outcome occurs in all of reality, then no. If it means determining your experience timeline through conscious choice, then yes. The question remains as open as it ever was. The European Space Agency is planning Euclid, a space telescope that will map billions of galaxies. Launch occurred in 2023. Data collection is underway. Results will arrive throughout the late 2020s and early 2030s. Euclid will reveal the large-scale structure of the universe with unprecedented clarity. If anomalies like the cold spot have structural patterns we cannot currently resolve, Euclid might detect them. NASA and international partners are developing the Nancy Grace Roman Space Telescope. Launch is scheduled for the mid-2020s. Roman will conduct infrared surveys of the sky, measuring distances to hundreds of millions of galaxies. These measurements will map dark energy's influence across cosmic history. If dark energy varies in ways that hint at parallel branes or leaking gravity, Roman should see the variations. Ground-based observatories are improving too. The Vera Rubin Observatory in Chile will begin operations soon. Its large synoptic survey telescope will photograph the entire visible sky every few nights. Over 10 years, it will create the most detailed map of the changing universe ever made. Anything unusual in the cosmos, whether gravitational anomalies or unexpected patterns, will show up in Rubin data. CMBS-4, the next-generation cosmic microwave background experiment, will deploy in the late 2020s. It combines detectors in Antarctica and Chile to measure the ancient light from the Big Bang with exquisite precision. The temperature maps will have resolution fine enough to reveal structures invisible to current instruments. If bubble collisions occurred, CMBS-4 will either confirm them or rule them out definitively. The Laser Interferometer Space Antenna will launch in the 2030s. 3 spacecraft flying in formation millions of kilometers apart will detect gravitational waves from the early universe. These waves carry information about events that occurred in the first instance after the Big Bang. Signatures of colliding branes or bubble universes should appear in the gravitational wave spectrum if they exist at all. Quantum technology advances rapidly. Companies and research labs worldwide are building more powerful quantum computers. Current systems have around 1,000 qubits. Next-generation devices might reach 10,000 qubits or more. At some point, quantum computers will become complex enough to test predictions from the many worlds interpretation directly. They might reveal computational processes that only make sense if parallel branches exist. Particle physics experiments continue searching for extra dimensions. The Large Hadron Collider has not found evidence yet, but upgrades could change that. Higher energy collisions might produce particles that escape into extra dimensions, appearing as missing energy in detectors. Finding such particles would support brane cosmology and hint at nearby parallel branes. All these experiments will deliver results within the next 2 decades. We are entering an era where parallel universe theories transition from speculation to testable science. The data will either support the multiverse or constrain it severely. Either way, we will know more than we know now. The question of whether other realities exist might be answered in your lifetime. The cosmic bruise might be explained. The quantum computer might remember existing in multiple states. The gravitational wave detector might catch echoes of another universe. Or we might discover the multiverse's illusion, that our universe stands alone, that the fine-tuning and quantum weirdness have prosaic explanations we have not thought of yet. Within 2 decades, we will know. The experiments are launching, the telescopes are building, the measurements are planned. The answer is coming,